As we saw in my last diagram, you can use an LC circuit to emit electromagnetic waves from something like an antenna. Far away from the emitter, we think of electromagnetic waves as plane waves or traveling sheets of electric magnetic fields. So you think of these as sheets of an electric field that travel along through space. In my diagram here, you can think of the electric field as going from the bottom to the top of the board, and it's going from zero and gradually getting stronger to a maximum value, and over time it oscillates. With Faraday's law, as a result of Faraday's law, if you have an electric field going in one direction and changing, you'll have a magnetic field going in an opposite direction, perpendicular. The new result here is that you'll also have the direction of propagation. Which way is this wave going is a right-hand rule or perpendicular to that. And so if electric field's going up and down, magnetic field goes side to side. The direction of propagation, which way is the wave going, is perpendicular to these sheets of electromagnetic field. This, as we're going to see in the next module, allows us to simplify light waves down to an arrow or a ray. And so you can picture light waves as these sheets of field, or you can picture of it as an arrow or a ray that carries energy in the same way. I'm not going to go too much further into the details of this, but one of the main results of looking at plane waves, electromagnetic waves, when you put this into the wave equation that we talked about at the beginning of the year, the main result is that the speed of electromagnetic waves, C, is related to the magnetic permeability and the electric permittivity. These are constants that we've seen with Ampere's law and Coulomb's law. To remind you, the permeability is 4 pi times 10 to the minus 7 Tesla meter per ampere. And the permittivity, this is in a vacuum. If it's going through glass or something like that, it's different. But in a vacuum, this is 8.85 times 10 to the minus 12 farad per meter. Put these together, work out the units. What you're going to find is the speed is 3 times 10 to the 8th meters per second for any electromagnetic wave. The theoretical description of this, putting it into the wave equation, coming up with this derivation, was Maxwell. And then experimentally, this was shown to be true by Heinrich Hertz, who set up something like what we saw earlier with the LC circuit, set up a transmitter and receiver at different parts across the room, and can verify the speed of light is 3 times 10 to the 8th meters per second. Electromagnetic waves are essentially traveling at this, or are basically invisible light waves. Here I'd like to show you a couple of nice looking simulations of these plane waves and LC circuits. So if we go to falstad.com, he's got a bunch of these nice simulations, all kinds of different things, 3D waves applet, and we can choose to look at, let's see, plane waves. So we think of plane waves as sort of these sheets of electric field and magnetic field. And so here The green and red are supposed to represent positive and negative sheets of electric field propagating through space. And so hopefully that gives you a little bit of a better visualization. And if you want to play with some of the different simulations, he's got hundreds on here. This is a simulation of an RLC circuit. So we have a inductor, capacitor, and a resistor, and then the dots represent current going through and oscillating in the system. And as you can see, it's sort of slowing down, so we can charge it back up. And in doing that, that charges up the capacitor. Open that up, and you can see the oscillation of the current through the circuit. Since there's a resistance, that has a damping effect, and you can see the current slowing down over time. If I increase that resistance, it slows down a lot. If I decrease the resistance, charge it back up again, it'll take much longer for those oscillations to damp out. So hopefully that helps you to illustrate some of these different things we've been talking about.